All right, next example. We only have two more examples, and then we'll be done with this packet. So here we go. It says consider the differential equation given by dy dx equals x over y. On the axis provided, sketch the slope field. All right, that's good. And then we want to do the solution point or solution through the point 0, 1. And then we'll find that particular solution through the point, right? F of 0 equals 1. That means through the point 0, 1. And then we'll basically do the same thing, but for a different point. We'll do 0, negative 1, and then we'll find that particular solution. Okay, but it also is going to start with doing the slope field. So let's go do this slope field first. I always like to look for the easy ones. So let's see. The derivative will be 0 if x equals 0. So anywhere the x value is 0, you know the slope's going to be 0, and the derivative would be undefined if the y value equals 0. So any point on my y-axis, the slope's going to be 0. Any point on the x-axis, slope's going to be undefined. Now you have to be careful. Undefined slopes, sometimes they'll tell you to do little vertical lines for the undefined, so that's vertical. Kind of hard to tell, but that's vertical. Or sometimes you'll just leave them blank. A lot of the times the question will tell you leave them blank, or the question will tell you do a vertical line. I'm just going to leave them blank, but I'm going to write a little note that says, hey, like these points where the slope is undefined, I'm not going to do the vertical lines. I'm going to leave them blank. But I'm not leaving them blank and having it look like I just didn't do it. But all of these points here, they're going to be left blank because at those points the slope is undefined. All right, well, let's go through and let's do it. All the other points on the y-axis are going to have a slope of 0. So everything on the x-axis, right? Everything here in this row would be undefined. So I'm going to leave all those blank. Then everything else, we're just going to test them. All right, so let's go through and let's test all these slopes. It's just x divided by y, so it's pretty easy. Here, if I have y equals x, well then y, if x and y are the same time, then x divided by y is going to be 1, right? So everything on here, the point 1, 1, the slope will be 1. Then at 2, 2, the slope would be 1. So anywhere on the line y equals x, the slope is going to be 1. If you have y equals negative x, well then the slope's going to end up being negative 1. So this point will be negative 1. So with that one, that one. So we have a couple of pretty easy ones. We found the 0 slopes. Those are all the points on your y-axis, excluding the origin. We have the undefined points. Those are all the points on your x-axis, including the origin. And we're leaving those, we'll leave those undefined ones. We're leaving them blank, which is all the ones on the x-axis. So we found the slopes of 1 and then negative 1, and then the rest of them we're just gonna plug it in. All right, so here it's 2 divided by 1. So this point right here would be a slope of 2. So you're kind of aiming to connect those 2 points. So I don't know, it's kind of close. And then over here would be 3, so steeper. This would be 3 over 2, so that's going to be 1.5. So oops, I don't want to do that. So that's going to be like a little bit less than 2. So I don't know, something more like that. And then we could do everything else. This is going to end up being a negative 2. This is going to be a negative 3. Then that's a negative 1.5. And then kind of the same thing. This right here is going to be 1, 2. So that's a slope of 1/2. And then this is going to be, let's see, that's 1, 3. So that's going to be 1/3. So it's going to be shallower. And then this would be 3, 2. Okay, so we can kind of see that there's this pattern. This was negative 1, 0, 1, 2, 3. This was 0, 1/2, 1, 1.5. So I know like this pattern is going to continue. That was 3, 2, 1, 0, negative 1. This is going to be negative 2. This is going to be negative 3. This is going to be a negative 1/2. That's my negative 1. That's my negative 3/2. And then this is 1. That's 2/3. That's 1/3. That's 0. This is going to be your negative 1/3. And then that'll be your negative 2/3. And then we can kind of use that symmetry to do the other side also. Here we had 3, 2, 1, 0. I guess those were all negative. Negative 3, negative 2, negative 1, 0. That's 1. This one's going to be 2. This one's going to be 3. And then the next row is going to count by 1/2. All right, here your step size. All right, come on. Step size was 1/3. I guess it should be like the change in the slope. Oh well. Let's change that. Here you were changing by 1/3. That middle row you were changing by 1/2. Here you were changing, not delta x, my change was 1. Kind of the same thing. That next row was all changing by 1, then it's going to be the 1/2. So let's just fill it in. This will be negative 1/2. That's your positive 1/2. Then that's going to be, let's see, 3/2. And then this one would be your 1/3, 2/3 negative, and here's the positive 1/3. So more or less, it's going to look like this. Again, if there's any doubt, you just pick the coordinates from any point. You just take, that one's kind of bad. Oh, well. Let's see if I can fix this one. You know what? I probably shouldn't. Because I'm just going to make it. Yeah, I just made it worse. Oh, well. Oh, well. But if there's any doubt in your mind about the powder, remember, you always just pick a point, take the x coordinate, plug it in for x. Take the y coordinate, plug it in for y. You can always just take the coordinates, plug them into the differential equation, and then that's going to give you what the slope at that point should be. Let's see if I can fix this one because it's bothering me now. Okay, yeah, it didn't really do anything. Oh well. So we've got the part A done, right? On the actually provided sketch the slope field done, right? Done with part A. Now let's look at the part B. Now we want the solution through the point 0, 1. So we want a particular solution. Remember, the slope field is the general solution. All of the potential graphs that have this as the derivative, x over y. But then specifically, if we want to go through a particular point, we could get that particular solution. Here's the point 0, 1. That point had a 0 slope, so that's going to end up being the minimum. And then the graph's going to go kind of upwards from that point, right? So that's going to be the spot where the slope is 0. And the graph's going to kind of go up like this. And then kind of the same thing on the other side. Okay, so it looks kind of like a parabola-ish. Yours may be a little bit steeper or a little bit shallower, but everyone should be something pretty similar to that, right? So we got the particular solution. Now on part C, it says, let's find what the equation for that particular solution is. So we're going to separate and integrate, right? Here's the one where the calculus is going to come in. We're going to separate, integrate, use the condition to solve for C, and then plug in all. Let's do that work down here. So I have dy over dx. That was x over y. Let's separate. So I have y dy equals x dx. So 1/2 y squared equals 1/2 x squared plus c. You can multiply by 2. And then the general solution here would be y equals plus or minus the square root of x squared plus c. Okay, so that's not terrible. Now let's go through and let's use the condition. We had f of 0 was going to equal 1, so we want positive, right? That's a positive 1 value. So I know not y. The positive 1 is going to have to be equal to the positive root. Let's see, I had 0 squared plus c. So 1 is going to be equal to the square root of 0 plus c. That means my c value is going to have to be 1. Okay, so that's great. We got this equation for this blue curve. Let's plug it in. Yeah, the general solution was plus or minus, but now in particular, the one that's going to go through the point 0, 1, it's not plus or minus, it's just going to be the positive root, and then it was x squared plus 1. So that would be the equation for the green graph we have going through the slope field. We have the positive root of x squared plus 1. Now let's do this same process. I guess I like to do my little checks. That part's done, right? Very good. Now let's go through and let's do the same thing, but for a different point. Now let's go through the point 0, negative 1, which would be right here. So that's also going to have a 0 slope, and then it's going to kind of curve like this, kind of curve like this. And if we're looking at the relationship, right, we're done with that part. If we're looking at the relationship between the graph from part D versus the graph from part B, they look symmetrical, right? The B just looks like the vertical reflection of this one in part D, right? It's like the two different parabolas, really. It's like a hyperbola, right? Remember your conic sections from pre-cal. I know you hated them, but there it is, a hyperbola. It's like the two parabolas that open in both directions. This is a vertically opening hyperbola. You have the top part with the positive y values and the bottom part with the negative y values. All right, let's go through. Let's use this condition, right? It's that same point. Let's solve for C, and let's find this equation. Now, all of this stuff, up to this point, all that's the same. Now, the only thing that's going to be different is that now we're going to use f of 0 is -1. So I'll have -1 is going to be equal to, and I'll need not the positive root, I'm going to need the negative root, because the only way that's negative is if you have the negative out in front of the radical. Then I had 0 squared plus c, negative's going to cancel, so I have 1 is equal to 0 plus c. So again, the c value is going to have to be 1, but the equation for the blue curve, I'll do it right here, it's going to be the negative square root of x squared plus 1. So looking at these two equations, right, the ones in the box, you have the y equals positive root of x squared plus 1, that's the green curve, the one above. Then you have the y equals negative square root of x squared plus 1, that's the blue curve. It makes sense, like algebraically we know the relationship between those two, like since I have the negative, it's just a vertical reflection. Graphically, the two things we can tell look that same transformation, right? They're both vertical reflections of each other, so that should be true both visually in the graph and also with the corresponding equations. So we had to do the slope field, easy. Then we did a particular solution, right? Easy. Then we had to use that condition to separate, integrate, solve for C. That took a little bit of work, but we should know how to do that by now. And then really parts B and D and E, that was the same as B and C. We just did it with a different point. And we could do this like a lot more. We could do this any point. We could separate, integrate, and we could use that new point to solve for C and find that third equation or that fourth equation or so on and so forth. The general solution represents all of the curves that would go through the slope field. But if you have a particular solution, make sure you just go through the point that it tells you, then you just flow the rest of the graph through the slope field. So separate, integrate, use the condition to solve for C, finish all the algebra. We know how to do all that good stuff. Okay, let's clear all this stuff, and then we're actually going to skip this one. I kind of want to just cut it out of the notes. I'm not going to do it probably in future years. If you have my notes packet that I gave you in class, this example is probably not even going to be there. If you're curious about it, it's probably there in my answer key that's posted in the PDF. But I plan on just cutting that out of my notes, so future generations won't even have it. But yeah, it may be in your notes for now, but I'm going to skip it. I don't want to do it. It's pretty much the same. I don't want to do it though. Let's just skip it, and then let's move on to the last example. All right, here we go. Where's my little arrow? Where it is? Where is it? There it is. It's hiding from me. The last example. All right, here we go. Let's get it kind of towards the top, and then let's do purple. All right, consider the differential equation. dy dx equals 2x minus y. Part A, sketch the slope field. Okay, so sketch the slope field and the solution curve through the point 0, 1. I always like to make sure that I'm going to answer every part of the question. So it says sketch the slope field and the solution curve through the point 0, 1. So I've got two things to do, right? Slope field and a particular solution through it. And then we'll worry about part B later. I don't want a tiny eraser. Let me change that a little bit. All right, here we go. Let's go through and do the slope field. I always look for the easy ones. So let's see, if x and y are both 0, then 0 minus 0, that'd be 0. Okay, so we know the slope at the origin. Oh, come on. So annoying. Sorry. Change it to the pin. Yep, it's on the pin. Now I can write it. So the slope there is going to be 0. And then let's see, if I have any other points that are going to be 0, how about the point right up here? Like that would be the point 1, 2. If I did 2 times 1 minus 2, ooh, that would be 0. Right? Remember, you could always just take that differential equation, which is 2x minus y, and if you set it equal to 0, we're going to figure out that, hey, any point on the line of y equals 2x, which y equals 2x, right? It's going to go through the origin, but then we'll go up 2 over 1, up 2 over 1, right? That line y equals 2x looks like that, but it has the slope of 2 instead of the slope of 1. But any point on that line would end up having a 0 slope. Oh my gosh, I didn't want to do that. Come on. Okay. Just have to erase it manually. How about that, Steve? Okay, very good. So there we go. That point is going to have a slope of 0 also. and then that one. Those are the only 2 points we have on that line y equals 2x. Now let's just test the rest of them. This is not a very big grid. It's only a 4x3. So there's only 12 dots. We got 2 of them, 10 more dots. Let's just plug in all the coordinates and let's go do it, right? The smaller the grid, this one's only 12, probably the harder the pattern's going to be. If it's a really big grid, then there's usually going to be a pretty nice pattern. But when all else fails, just pick a point, plug the coordinates into the differential equation, figure out what's the slope of the graph at that point, draw your little line segment. All right, so let's just go for it. I'm going to go on the x-axis. So this one, it's the point -1, 0. So we've got 2, -1, -0. So it's -2 minus 0. So that's -2. So, you know, ish. Let's do this point, which is 1, 0. So 2 times 1 minus 0, 2 minus 0. Let's do, okay, so that was -2. That's 0. This is going to be a +2. Let's look at the next one, which is 2 times 2 minus 0, right? 2x minus y. So that one's going to end up being 4. So it was -2, 0, 2, 4. So that one was counting by 2s, right? This one does have a pattern. It was 4. Let's go up and let's look at the next row, right? When in doubt, just test everything. Let's go look at this one, which is the point -1, 1. So 2, -1 minus 1. That's going to be -3. So this was a slope of -2. This one's going to be even steeper. So it's going to be -3, more or less. If I did the point right next to it, that would be 2 times 0 minus 1. So it's going to be 0 minus 1. Oops, 0 minus 1 equals -1. So this one's going to be a slope of -1. And then here, if we test the next point, that's the point 1, 1. 2 times 1 minus 1. So that's 2 minus 1. That's 1. Okay, here the step is also 2. But here was -2, 0, 2, 4. The step size on that next one is also 2, where the step of the slopes is also 2. But it was -3, -1. This is a +1, and this one's going to be a +3, right? That slope is still going to go up by 2 each time. It's just counting. It just started at a different spot. Okay, here we go. Let's go look at this last row. I guess I should erase all this stuff. All right, so let's do this. Let's just do this point. Here we go. That's the point 2, 2. So 2 times 2 minus 2. That's 4 minus 2. That's 2. So at this point, the slope is 2. Okay, so here we go. Slope of 2. Okay, more or less like that. Remember, that was 4, 3, 2. Let's see, that one was 2, 1, 0. So I think I can kind of see this pattern. That was 2, that was 0. Let's just kind of guesstimate it. Or if you're ever in doubt, right, just plug it in. 2 times 0, yeah, I guess it would be -2 for this one. That's the point 0, 2. So this is going to be -2. And then this one's going to end up being -4. Pretty similar. There is some symmetry involved. There's just a little bit weirder to see what that pattern is. But when in doubt, you can always just test all the points, right? You can always just test all the points by plugging in the different coordinates and then drawing the little representative line segments through that point with that slope. Okay, so we got the slope field done. Now let's do the particular solution through it, right? So particular solution through the point 0, 1. Well, there's the point. Remember, somewhere on that line, y equals, the slope is going to be 0 on y equals 2x. My particular solution is going to cross that line. And wherever it crosses that line, that's where our slope will be 0. But here it was a slope of -1. And then kind of it's going to do something, I don't know, more or less like this. And it's going to go, it doesn't look terrible. It doesn't look great, but it doesn't look terrible. All right, so there we go. We did the first part, which is the slope field, then we did the particular solution through it. Very good. Okay, so we're done with part A. Now part B is kind of a little bit weirder, right? We did that, we're done with part A. Let's go look at the part B. It says the solution curve that passes through 0, 1, aka the orange graph that we just did, it says it has a minimum point at x equals ln of 3/2. Well, I can clearly see that, yes, that particular solution has a minimum. And we know that minimum point, right? That minimum is going to be on. Minimum is on y equals 2x because that's where your derivative is 0. Right? Right? So we know that coordinate point is going to exist, and it's telling us the x value of that point. Right? If we're looking at that point, the x coordinate of it is ln of 3/2, and it's asking, what's the y coordinate of that point? Well, usually, if you have the x and you're trying to figure out the y value, typically what you would do is you would just take the x and you would plug it into that equation. Right? If I had the equation for that orange function, I would plug the x value into the function, and it would give me the output, the y value. But I don't have the equation for that orange curve. And that differential equation is not separable. So it would not be possible for me to separate and integrate and to use the condition to solve for c because it's not separable. But luckily, we don't really need to, right? Remember, we have the x coordinate. And what else do we know about this point, right? Since it's a minimum, we know the derivative has to be 0. So which equation can we plug it into? We don't have the original equation for that orange curve, but I do have the differential equation, which works for not only the orange curve, but it works for every curve in that slope field. So let's plug in to the differential equation. Right, here's the work for part B. We know the slope, dy dx, that's going to be 0 at the point. And then right at that point, we know the slope is 0. We know the x value. We want to know the y value, so let's plug it in. The slope is 0. Then we have 2. Plug in the x value, ln of 3/2 minus y. If you have the original equation for that orange function, you can plug in the x into the y. There you go, you'd be done. Since I don't, we're going to have to use the only equation we do have, which is the differential equation. I know what the slope is at that point. It was 0 since it was a minimum. I know what the x value is, and so we're just going to plug in the two things that we know to solve for the one thing that we don't know. So this y coordinate is going to end up being 2 ln of 2/3. And then that was it, right? So that's the y coordinate. So that point right here, it has the point, what is it, ln of 3/2, and then the y coordinate would be 2 ln of 3/2. AKA, if you didn't want to leave it like this, you could write ln of 4/9. Is it 3/2? Or it was 3/2. I don't know why I have the 2/3. Why did I switch it right there? Oops, no, I don't want to do that. No, come on. I don't know why I switched it right there. Sorry, that was bad. It was definitely ln of 3/2. I don't know why I switched it. So ln of 3/2. At least I caught it relatively early. So yeah, 3/2. So then if I took this 2, right, I could take that 2 and I could stick it as an exponent. So I could have ln of 3/2 squared. So then I would have 9/4, not 4/9, 9/4. If you wanted to leave it like this, that would be fine. You could have also ln of the 3/2 and then ln of the 9/4. Either one of those would be fine, doesn't matter. But that one's a little bit weird because we don't know what that equation for that orange curve is. But you don't really need to know it. You have the differential equation, that's all you need. You just had to recognize that at that point, since it was a minimum, the slope was 0. So I really knew this thing, and I knew the x value. And so if I have an equation with 3 unknowns, but I can plug in 3 of them, that's good. Just solve for the one that you're missing. Okay, so here we go. Last part, we got part D. Let's do part C. It says that y equals f be the particular solution that goes through that condition. So f is going to be my orange curve. It says write the equation for the tangent line to f at x equals 0, 1, and then use it to approximate the curve. Right, so here's my tangent line, right? It's going to go through this point. Let's see, the tangent line more or less would look like this, right? So here's my tangent line going to go through the point 0, 1. Let's go get the equation for this tangent line. Remember, y minus y1 equals mx minus x1. That point slope version of the line should always come to your brain whenever we see those 5 words. Equations for or of the tangent line. We have the y coordinate, so I've got y minus 1. We know the slope of the graph at that point. That was a -1 slope, right? So at that point, we had the x, we had the y, we know the slope at that point was -1. So -1, x minus 0. You could leave it like that, but since we have to use it, right, we're going to use that tangent line. I'm going to go ahead and just simplify it. Y is going to be equal to -x plus 1. So there is the equation of the tangent line. Right, so that's done. And then let's use it to approximate where the function is. So let's see, y of -0.4, it's going to be -0.4 plus 1. The two negatives would cancel, so that's going to give me 1.4. So the tangent line is equal to 1.4. Right, if I look just slightly to the left, right, -0.4 would be up here. That point, you can see that's going to be above 1. So we really can't tell for sure what the original function is, but we know the tangent line is probably fairly close to it. The tangent line is equal to 1.4, therefore f of -0.4 is going to be about 1.4. Remember, tangent line is, therefore the original function is about. Right? Tangent line is equal to 1.4, so f is going to be about 1.4. So we got ourselves the equation of the tangent line. Now we've used that equation to approximate f. And then here the last part says find the second derivative in terms of x and y, and then use that to determine whether it doesn't tell us to use it, but if it says find the second derivative, it's going to want us to use it to determine whether the approximation in part C is less than or greater than the real exact function value. Now, let's take a quick little eyeball check. Let's look. Here was the point on the tangent line, which we know that point on the tangent line was 1.4. Here's the point on the function, right? That's f of 1.4. Now, we know f of 1.4 is probably, actually, it wasn't f of 1.4. It was f of an x value. It's -0.4. So we know that true function value and that approximation from the tangent line. We know that they're probably pretty close together. And from the graph that we sketched, it looks like the function ends up above the tangent line. So it looks like my estimation is going to end up being a little bit less than the real function value, right? It looks like I had an under approximation. But we can't just go based on the eyeball test of my diagram, because we kind of just sketched that slope, that graph through the slope field. That's not 100% accurate. So we're going to want to go ahead and actually confirm whether it's concave up or concave down, which will tell us the answer definitively. So let's do this work over here. Right? Let's find the second derivative. We know the first derivative is 2x minus y. Therefore, take the derivative again. The derivative of 2x is 2. And the derivative of y is y prime. But we don't want it to be in terms of y prime. So I'm going to go plug in, right? What is y prime equal to? 2x minus y. Distribute the negative, so we're going to end up getting this second derivative is 2 minus 2x plus y. So there's your equation. Oh no, what am I doing? No, stop it, go back. So here's the equation for the second derivative. And then it says, all right, let's determine if my estimation, the 1.4, if that's too little or if that's too big. Is my estimation less than the real function value or greater than the real function value? All right, so let's check it out. Now, the second derivative, at the point that I know, right, everything was based on this point, 0 and 1. So when x is 0 and y is 1, that's the point where we built the tangent line. That's kind of everything is in reference to. Let's plug in that one coordinate at the point we know. Let's see what the concavity is. So that second derivative would end up being 2 minus 2 times 0 plus 1. That's 0, 2 plus 1, that's 3. So we get the second derivative is positive. And since the second derivative is positive, right, that means the graph is going to be concave up. And since the graph is concave up, then we can definitively conclude that, yes, like this curve, it's going to peel upwards and away, right? Since it's concave up, we know the graph is going to peel upwards and away. The tangent line just keeps going, right? It has 0 concavity. It just keeps going with that same -1 slope. But since the curve, we know that it's concave up, the curve is going to peel upwards and the curve will end up above the tangent line. So it says find the second derivative. We did that, right? That was right here. Then it says determine whether the approximation is less than or is greater than f. So we've got everything we need, right? Now we just need to answer it. 1.4 is going to end up being less than the true function value. And then the reason would be because f is concave, not concave down, f was concave up. So really you would want to show, obviously this, because it said find the second derivative, then you'd want to check, hey, is the second derivative positive or negative, which means is it concave up or is it concave down? And then that'll tell you, hey, since it's concave up, the function ends up above the tangent line, therefore my approximation is going to end up being less than the real function value. The explaining the reasoning, you would want to say something about the graph being concave up, or you could say something about the second derivative being positive. Okay, so that one's a little bit weird, but the second derivative we use to answer concavity. Concavity will tell us, hey, does the function peel upwards and away, or does it peel downwards and away from the tangent line? Then if you're thinking about that, it should actually kind of reinforce and it should mesh with the stuff we got in the diagram, but don't always go just based on the eyeball test of the diagram, right? Use the second derivative and the concavity to prove it and to confirm it. Since the second derivative was positive, the graph is concave up, therefore the real function value, right, on the point on the curve is going to end up above the tangent line. Therefore, my approximation is less than f of negative 0.4. Alrighty, that's it. I know that's a lot of stuff. This lesson goes, or this whole unit goes pretty quick. It's very algebra heavy. Hopefully it's okay.